Okay, Assalamualaikum warahmatullahi wabarakatuh. Okay, now we learn for topic 2. Okay, topic 2 in part A. Okay, hydrostatic pressure and buoyancy. Okay, now we look at the learning outcome. Okay, at the end of this chapter, students should be able to understand and analyze hydrostatic pressure and buoyancy and list out and apply equation of hydrostatic pressure and buoyancy. Okay, now we look at the pressure head. Okay, pressure is defined as a normal force exerted by a fluid per unit area. Pressure is defined as a force per unit area and the unit of newtons per square meter. Okay, which is called a Pascal. That is 1 Pascal is equal to 1 Newton per meter square. Okay, now we look at the other units for pressure. 1 bar is equal to Pascal, convert to Pascal to megapascal and kilopascal. Okay, 1 atmosphere. Okay, convert to Pascal and bars. Okay, and kg force per square meter. Okay, so per square, okay, centimeter. So convert to Newton per centimeter square, Newton per meter square, convert to Pascal, convert to bar and atmosphere. So they have the 3 units for pressure: bar, standard, atmosphere and kilogram force per square centimeter. Okay, now we look at the 2 example here for the pressure based on these 2 person with the different weight but with a area of feet. Okay, so the pressure equation is equal to weight divided by the area. This is based on unit P as a unit. Okay, so the normal stress or pressure on the feet of a chubby person is much greater than on the feet of a slim person. Okay, so now we look at the actual pressure at a given position is called the absolute pressure. Okay, and it measured relative to absolute vacuum. Okay, so we look at the next previous slide. Okay, based on absolute pressure and absolute vacuum. Okay, most pressure measuring devices, however, are calibrated to read 0 in the atmosphere, and so they indicate the difference between the absolute pressure and the local atmospheric pressure. So this difference is called the gauge pressure. Okay, so pressure below atmospheric pressure are called vacuum pressures. Okay, vacuum pressures and are measured by vacuum gauge that indicate the difference between the atmospheric pressure and the absolute pressure. So now we look at this figure here. Okay, to get the P absolute here, based on the P absolute here, so the pressure, atmosphere pressure minus by P vac, so we get the P absolute. Okay, so based on this equation, so P absolute is equal to P atmosphere plus the P gauge. So this is the equation for this figure. Okay, now we look at the example 2.1. So the vacuum gauge connected to a chamber with 5.8 Pascal at a location where the atmospheric pressure is 101.3 kilopascal. So we use this equation to determine the absolute pressure, okay, in the chamber. So P absolute is equal to P atmosphere minus by P vacuum. Okay, so we just put the given data here and we get the P absolute. Okay, so now we look at example 2.2. Find the absolute pressure in kilopascal unit if barometer shows the reading of 60 kilopascal. So given that barometer reading at sea level is 740 mmHg, okay, the specific gravity of mercury is this one. So the data given is gauge pressure, okay, barometric reading, okay, and mercury specific gravity. So now we look at that to get the pressure, atmospheric pressure, so we use the equation of density of mercury times by the G times by the H. Okay, so to get the density of mercury, so Sg mercury times by the density of water 1000, okay, times by the G 9.81 times by the H 740 divided by 1000, because convert to meter, so we get the P atmosphere is pressure atmosphere is 98.73 kilopascal. Okay, so now we use the equation of the P absolute is equal to P gauge plus P atmosphere. So you just put the value here and we get the P absolute is 158.33 kilopascal. So this is the value that you get from the equation. Okay, so now we look at the variation of pressure with depth. Okay, so with the depth of this, okay, from the water level here. Okay, so pressure in a fluid increase. Okay, a fluid increase with depth because more fluid rests on deeper layers. Okay, and the effects of this extra weight on a deeper layers is balanced by an increase in pressure. So the pressure, okay, will increase with the depth. So that's why it's called variation of pressure with depth. So the pressure of a fluid at rest increases with depth as a result of added weight. Okay, now we look at to obtain a relation for the variation of pressure with depth. Consider a rectangular fluid element in equilibrium. Okay, so we know that the forces is equal to mass times by the area. Okay, is equal to 0 because we want to force balance in the vertical x direction, z direction give. Okay, so look at this consideration of rectangular fluid element in equilibrium. So the pressure one, okay, times by the delta x. So we get this equation. Okay, so pressure 2 times by the dx, so we get this equation. Okay, and this for rectangular fluid element, so we get this equation. So this is based on the balancing for this rectangular fluid element equilibrium. So in pressure, force to pressure. Okay, so now we look at this point here. So if we take point 1 here, okay, to be at the free surface of a liquid open to the atmosphere, where the pressure is the atmospheric pressure, P atmosphere. So then the pressure at a depth H from the free surface becomes P2. Okay, this is the H. So based on the previous slide, so we know that the pressure will increase with the depth, variation of pressure with the depth. Okay, that's why we know that the depth is H here. Okay, the pressure at point 1 is pressure atmosphere. Okay, to get the pressure at point 2, so you must include the pressure 1 plus the pressure in this fluid. Okay, rho GH here. So that's why you get the pressure at 2 is P atmosphere, okay, plus the density of this fluid times by the G times by the depth H. Okay, so that's why we get the pressure at point 2 is equal to pressure atmosphere plus pressure gauge. So this is also called pressure gauge. Okay. Okay, so we get this one and we get the P gauge here. Okay. So now we look at this concept of the variation of depth with the same level, water level here. Okay. Okay, and the same level here. Okay. So from this equation, from this figure, okay, we know that the point are at the level A here. Pressure at A is equal to pressure at B, equal to pressure at C, equal to pressure at D, E F, G. Okay, because we get the pressure at A, B, C, D, and E is equal to the pressure from the P atmosphere plus the pressure gauge here. Okay, pressure gauge. Rho GH, because the liquid is water, okay, with the same level and with the same water and the same depth of water. So using the concept of Pascal law, so this pressure at the same level is same, okay. But for the pH here, okay, pressure at H is not equal to Pi. Okay, it is because the pressure at H is have two different liquid, okay, water and mercury. Okay, but for the I here, they just only have the water. So that's why the pressure at H and the pressure at I is not equal, not the same. Okay. Okay, so pressure in the fluid at rest is independent of the shape. Okay, for cross section of the container. Okay, for the cross section of the container, it changes with the vertical distance but remains constant in other direction. So therefore, the pressure is the same at all points. So the pressure is same at all points on a horizontal plane in a given fluid. Okay, so this is the concept for variation of pressure in depth. Okay, now we look at this concept here. Since there can be no shearing forces for fluid at rest, so there will be no accelerating force. So the sum of the forces in any direction must therefore be zero. Okay, so the forces acting are due to the pressures on the surrounding and the gravity force here. So they have the PS here, pressure at this point S, pressure for X direction, the pressure for Y direction. So this is PS is pressure for Z direction here. Okay, so for Z direction there must be include the two directions, so just include the X direction and Y direction. Okay, so the PS is X direction only and the Y is Y direction only. So that's why, so in this force due to PX, okay, so we know that the PX pressure at X is equal to PX times by area ABEF. So we get the PX dy dz. Okay, so horizontal component of force due to PS, because they have only two direction, X direction and Y direction. So this is concept horizontal component is for Y direction. So we get the PS, okay, is equal to negative because the arrow is based on, okay, draw down here is negative, go to the left side here is negative. So that's why we get the negative here. Okay, so we get the PS is equal to negative PS times by dy dz. So this is called for the component X direction. Okay, so similarly in the Y direction, force due to Py is equal to Py dx dz. So since dx, dy and dz are very small quantities, so dx dy dz is negligible in comparison with other two vertical force terms, and the equation reduced to component of force due to Ps is negative of PS times by area A, B, C, D cos theta here. So we get the negative PS dx dz. Okay, now we look at the actually, so this is called Pascal law. Okay, no need to worry about this, the theory, so on. Okay, so you just must know that the Pascal law. So we know that at the same direction horizontal, so we know that Px is equal to Py is equal to Ps. So the pressure at that point is same in all direction. So this is called Pascal law. So this applies to fluid at rest. So use the Pascal law. So now we look at this concept here. Okay, the point with the same level here. Okay, pressure at point 1, okay, and the pressure at point 2. Okay, so we just use the Pascal law. So we must mention here pressure at point 1 is equal to pressure at point 2 here. Okay, so we know that the pressure 1 is equal, must include the area 1 and the pressure 1 here. So we know that the forces of F1 is equal to P1 times by the A1. Okay, force 2 is equal to pressure 2 times by the A2. So that's why pressure 1 here, okay, based on this equation here, to get the P2, we must know that the force 2 divided by the A2. Okay, so this one for P1, so F1 over A1. Okay, so that's why you get this equation. Okay, from P1 is equal to P2 here, so F1 A1, F2 A2. So you convert from this one to this one. Okay, F2 over F1 is A2 over A1, or you want to change also using the F1 over F2, so you get the A1 A2. Okay, so you can use this concept, whether you can use this one or you can do this one. Okay, so the lifting of a large weight by a small force by the application of Pascal law. So this is called Pascal law. Okay, so now we look at example 2.3. Okay, what is the pressure difference in 1 meter of seawater compared with 100 meter of seawater? Okay, so with atmospheric pressure is 1.013 times by 10 power of 5 Pascal. So they give you the atmospheric pressure is this value. Okay, so now at the 1 meter, okay, so actually this example is, this is the figure. Okay, the figure, actually the figure for this concept is at this. Okay, with the H. Okay, H is 1 meter and 100 meter. Okay, and we get this is P1, pressure at point 1, and this is pressure at point 2. Okay, so that's why this is P1 is equal to P atmosphere. Okay, so that's why to get the pressure at 2 with the depth of 1 meter, okay, so you must find the P2 is equal to P1 plus rho GH. So this is P atmosphere. Okay, plus the density of water. Okay, the density of water. Okay, so just complete here is, okay, so times by the G 9.81 and times by the H is 1 meter. So you get the value here. Okay, so look at the at 100 meters, so you get the pressure at 2 is equal to pressure at 1 plus rho GH. Okay, so you just put the pressure atmosphere plus the density of water here. Okay, just correct here. Okay, and so you get the 9.81 meter per second squared and times by the H 100 meter. So you get the value of this P2. Okay, so the just pressure difference between the 100 to 1 meter, so you just minus. Okay, so you get this value. Okay, 9.75 times by 10 power of 5 Pascal. Okay, so now we look at the example of 2.4 here. Okay, figure shows 4 different fluid inside a glass container at 20 degrees Celsius. So if atmospheric pressure and absolute pressure at the surface and bottom are 101.03 kilopascal and 231.3 kilopascal, find the specific gravity of olive oil. Okay, so this is the SAE here. So SAE with the specific gravity here. So the SG is given. Okay, so just look at the solution here. Okay, so the P atmosphere. Okay, for the SG for SAE is 0.92. Okay, you just times by the density of water, times by the 9.81, and times by the depth of water. So you get the pressure at this fluid. So you get this value. Okay, so you must do it step by step. Okay, first you must find the pressure at SAE liquid oil. Okay, then step 2, you must find the pressure in water. Okay, so you just put the value here until you get the value of pressure of water. Then step 3, you must find the pressure in olive oil. Okay, but olive oil, we don't know the value of SG because you want to find the SG here. Okay, so just the pressure in olive oil in terms of SG. Okay, and then step 4, you must find the pressure in mercury. Okay, so just put the value here until you get the value of pressure of mercury. Okay, so note that for all these fluid, so you must P atmosphere plus P SAE oil plus the P water, P olive, and P mercury is equal to P absolute. Okay, so we put all the value here. Okay, with the P olive is in terms of SG. So you get the SG of olive is 1.4. Okay, so this is the concept step by step for different fluid in different depth. Okay, so you must do for this calculation. Okay, now we look at the pressure measurement with manometers. So the manometers, there's the 3 types of manometers. So there's the simple U-tube manometers, differential manometers, and inverted manometers. Okay, so look at the simple U-tube manometers here. Okay, so simple U-tube manometers here. So you look at this figure 1. Okay, actually this is figure 1. So this is figure 2. Okay, so you just look at use the concept of Pascal law. Okay, you just get the same level with the same liquid. So this is the same liquid, so you put here as the P1, pressure at this point 1 is same as pressure in the point 2. Okay, so we just put using the Pascal law, P1 is equal to P2 here. Okay, so now we look at the left side here for P1. So the left side for P1, so just include the pressure at A, at this tank. Okay, at this tank A. Okay, so the PA, pressure at A, plus the pressure in this gauge here. Okay, rho G H. Okay, so this pressure is using the rho G, and the H is H2. So H2. So now we look at the right side. Okay, so it's the PB, include the PB, and plus the rho G H1 plus H2. Okay, so this is the concept for this equation for this figure 1. Okay, so now we look at the figure 2 here. Okay, so as the same concept for Pascal law. Okay, so just put here, this is point 1, okay, and the point 2. So using the Pascal law, so the P2 is equal to the P1 here. Pressure at 1 is equal to pressure at 2 here. Okay, so we use equation here. Okay, now we know that look at this side here, pressure at 2. So pressure at 2 is based on P atmosphere. So this is actually, they have the P atmosphere here. Okay, P atmosphere plus the rho GH here. Rho GH. So that's why we get this equation. Okay, So now we look at this one. So this is actually for figure 1. Okay. So actually this concept, consider left and right side. Okay, P left and P right. Okay, P left and P left and P right. So we just P left is P1, P right is P2, pressure at 2. Okay, so P left, so step by step, so you must calculate first for Px left at the pressure at left. So Pa plus the density of the area, the density of liquid of A times by the G times by the H2, actually for this question, okay, for this figure, actually for this theory. Okay, so the text here is for this figure. Okay, now we look at, so now you solve the pressure at right. Okay, pressure at right. Okay, the depth, the P atmosphere. Okay, the P atmosphere is PB. Okay, PB plus rho G H1 plus H2. That's why we get this one. Okay, so if the P atmosphere is 0 as data, therefore, so just put the atmosphere is at 0. So they have no atmosphere here. So the PA plus density A times by the GH2, and the at right, okay, at the pressure at right, so there's just only have this equation, so no atmosphere. Okay, so you just put this one, so you get the PA is PB times by G times by H1 plus H2 minus density A times by the GH2. So this is concept for YouTube simple manometer, YouTube manometer. Okay, so now we look at example here. Okay, calculate pressure at A. To calculate the pressure at A here, okay, to get the PA. Okay, if H1 is, okay, H1 is 50 mm and H2 is 120 mm. So you must convert to meter. Okay, and the density of this A, density at this plane here, actually this is density at A. Okay, okay, so we get the density of water here is density at A, and the density of this B here, okay, mercury. Okay, so density of B. Okay, so density of B. So we get the, so we must find the, this is at the left, P left. So we get the as a P right. Okay, so you just use the Pascal law. So you just look, the P left is equal to P right. Okay, so the P left, this include the pressure at A plus the density of air, A. Okay, actually pressure for the A or water, pressure density of water times by the G times by the H2. Okay, you just put the value here until you get the PA plus P pressure at left is equal to PA plus 1177.2. Okay, and solve the pressure at right. So it include the P atmosphere plus the density of B or mercury, pressure, density of B or pressure of mercury times by the G times by the H1 plus H2. Okay, you just put the value here until you get the this equation. So now you just do this Px left and P right, x right is using this one. Okay, so the P, this is P left, this is the P right, so you get the PA, this value 21.44 kilonewton per meter square. So this is the solution for that figure. Okay, so now we look at example 2.6 here with the figure 2 here. Okay, measuring pressure with a manometer. So a manometer is used to measure the pressure in a tank here. Okay, in this tank with the specific gravity of 0.85. Okay, and the manometer column height is 55 cm. Okay, the here. Okay, so the atmospheric pressure is 96 kilopascal. So determine the absolute pressure with the tank. Okay, to get this one, P absolute pressure in this tank to get the P here. Okay, so now we just use the concept for PA, PB here. Okay, actually, so we use the pressure at A is equal to pressure at B. Okay, using the Pascal concept. So PA is equal to PB. Okay, so PA is include the pressure at A. Okay, okay, because the PA is include the pressure at here, PA here. Okay, so we just PA is equal to PB. We include the P atmospheric and plus the rho GH here. Okay, so that's why rho GH here. So you just put the value of P atmosphere is this one. Okay, and just put the density of mercury here, sorry, the fluid here, 0.85 times by the 1000. So we get the density of this fluid times by the 9.81 and times by the H. Okay, based on convert to meter, and you just use this unit to convert Newton per meter to kilopascal. Okay, so that because the atmosphere is in kilopascal, that's why you get the pressure at A is 100.6 kilopascal. Okay, so this is the solution for that manometers. So now we look at the differential manometers. Okay, so this differential manometers is to find the pressure difference. Okay, pressure difference based on pressure at 1 to pressure at 2 here. Okay, so now we use using the same concept of Pascal. Okay, so you based on PA must equal to PB. Okay, so that's why assume that PA is equal to BB. Okay, so now we look at the side here, left side here at the PA here. Highlight, we use the highlight. So you just look at the left side here. Okay, and this is right side here. Okay, so the left side, here is based on pressure at point 1. Okay, and also the height, the pressure at the gauge at this part here. So that's why pressure at 1 plus the density 1 here times by the G times by the A plus H, because the height of this is A plus H. Okay, so that's why you get this one and the P1 here for this side, left side at the PA. And from the side here, right side here, the PB here, so this include the point at 2. Okay, pressure at 2 plus density of 1 here. Okay, density of 1 here, and this is density 2. Okay, so that's why the density 1 plus the times by the G times by the A, and plus the density 2 times by the G and times by the H. So you get this one. Okay, so and you extend all the equation here, so you get this one. Until then you get the difference of pressure 1 to pressure 2, so you get this equation. So this equation for differential manometers, so based on this figure. Okay, now you look at this concept for this figure. Okay, so used to measure pressure difference between 2 points. Okay, based on 2 points A and B here. Okay, consider left and right side, left side and the right side here. Okay, so you just consider this is P left is equal to the P right. Okay, so you get the P left here. Okay, so P left here. Okay, this is consider P left, P right. Okay, so for the P left here, so this include the pressure at A. Okay, and also the include at pressure at this A gauge of GH2. Okay, so you get the for P left here. So look at the right here. So this include the pressure at B, and pressure at B here, and GH3, and also PA, okay, GH3 minus by H1. Okay, so actually the concept of PA or PB here, okay, actually this is at the A. So actually this at the same water, okay, so at the same liquid here, okay. So that's why we get the PA is the same here, PA and PA here. So because this is the same fluid. So that's why, so after you balance from the left and right, so you get this equation. Until the last equation, you get the difference, okay, the pressure difference between 2 points. So you get this one, okay, until you get this. So now you look at example here, okay. So the example here, they give you the density of water here with the fluid of, this is density of water, and also density of water, okay, and this is density of mercury, okay. So now we look at figure below shows differential manometer used to measure pressure inside a pipe. Okay, if PA minus by PB is the give you to this one, so to find the H, here, okay. So now you just also use the same concept of Pascal law, okay. So pressure at left here is equal to pressure at right, okay. So pressure at left is equal to pressure at right, okay. So now first you must look at the pressure at left, okay. Pressure at left is include the pressure at A here, pressure at A, okay, and plus the pressure water times by the G times by the H. Okay, we don't know the H here, so we just put here as the HA. Okay, we put here as the HA. Okay, and we put here as a HB as 1.6 meter here. Okay, so now we look here. So we know that the left side here, HA plus H. Okay, so just put all the value here until you get the equation for pressure in left, okay. So now you look at the pressure at right, sorry, the pressure at right here. So this include the pressure at B, pressure of this water, okay, pressure for the water, and pressure for this mercury. So that's why you get the pressure at B plus the pressure mercury times by the GH plus the pressure water, okay, with HA plus HB, okay, until you solve the solution here. Put all the value until you get the pressure in right is this equation. So now you just use for balancing for P left is equal to P right. So you just put here, okay. So P left is equal to pressure at right. So you put the solve the from the previous slide. So you put the here and the put for right here. So until you get the H is 0.844 meter. Okay, so you can calculate, okay, calculate from these equations until you get the 0.844 meter. Okay, so now we look at the inverted manometers. So inverted manometers is the manometers is below here, okay, so this inverted here. So mercury is used to measure pressure if fluid is low density, especially for oil. Consider left and right, so you must use the concept of Pascal law, okay. P left is equal to P right, okay. So now you look at the P left here, so this is P left, this is P right, okay. Pressure at left, pressure at right here, okay. So now you look first at the pressure at left here. So pressure at left, this include of the pressure in A here, pressure at A here, okay, because the fluid is go up to the point here, okay, so they must negative, okay, so there's the negative or density of, okay, density of area and GH2. Okay, so that's why you get the density of A times by the G times by H2. And also this one, okay, density of air GH1. Okay, you get this one. Okay, but neglect P density of air. So neglect of density of air. So there's no air here. Okay, so never mind. So just go through the pressure at right here. Okay, the pressure at right is based on the pressure at B. Okay, minus by the PAGH3 here. So they have the PAGH3 and also here PAGH1. Okay, they have the side here PAGH1. So you get this one. Okay, so we get the PB minus by density A times by the G times by the H plus H1, okay, from this equation. So hence that P left is equal to P right. So you just put from the left to right here, okay, until you get the equation for this inverted manometers is PA minus by PB. So inverted manometers is equal to density A times by the GH2 minus by density A GH3 plus H1s, okay, because we neglect the density of air, so there's no air in this side here, left side here, okay, no air here, okay. So this is inverted manometers. So now we look at the example here, okay, to find the pressure PA minus by PB, okay. So use the concept at the same level here, okay. So you use the left and the right side here. So you just look first at the left, pressure at left. So we know that it's consider pressure at A here, okay. Consider and also consider density of A here, okay. That's why we get the density of water GHA, and the HA is 1.625 meter, okay. So we get the value of pressure at left. Okay, now we look at the pressure at right here. Okay, just put the value until you get this side here. Okay, this you get the left and you get the pressure at right. Okay, and then you just put to this balance. Okay, use this equation. Okay, just put here, so we get the PA minus by PB, this value. Okay. Okay, now we look at the example 2.9. So this is more on multi-fluid manometer. Okay, it's the same point, so you must use at the same Pascal law. Okay, so we look at this one. Okay, using the same of the Pascal law here. Okay, we based on the P1 here and the P2. Okay. Okay, so we know that pressure at point 1 is equal to pressure at point 2. Okay, so you just put all the value here actually at the point 2. Okay, pressure at point 2, we can look at this one is based on pressure atmosphere minus, plus the pressure of mercury GH3. Okay, so this is pressure at 2. Okay, so and pressure at 1, so consider based on P1. Okay, consider for the density of water, density of oil, and so on until we get the value of this one. Okay, for P1. Okay, so P2 we get this one. But for this one, from the P atmosphere, so we go find the pressure here. Sorry, the density go to this side, left side here. So that's why they have the negative. Actually, this is the P2 here. Okay, P2 here. Okay, and then you solve the equation here, put all the value here until you get the pressure at 1 is 130 kilopascal. That's all. Okay, so that's all for this part A. So to be continued in part B. Okay, that's all. Thank you. Assalamualaikum warahmatullahi wabarakatuh.